Today I will talk about energy and power in AC circuits. So energy and power in AC circuits. So we want to know how much power and energy is delivered to elements. In DC circuits, the only element that we had was a resistor, but in AC circuits, we have a resistor, inductor, and capacitor, and we want to discuss the delivered energy and power to these three elements. First, we'll start by discussing resistor in AC circuits. Okay. We know that in like a sinusoidal steady state, the current going to a resistor is equal to a sinusoid signal which has a magnitude of Ia cosine of omega t. Okay, so this one is the current moving through a resistor. What is the power of the resistor? The power of the resistor will be, of course, Ri square. Okay, so it's equal to Ri because it is like a sinusoidal signal, we say It square. So it's equal to R instead of IR, we replace it with this value. So we will have I a square cosine of omega t square, which is equal to Ria square over 2 times 1 plus cosine of 2 omega t. This one is the power delivered to a resistor. What is the energy like delivered to a resistor? We know that the energy is the integral of the power. So we can say the energy delivered to a resistor is equal to integral from 0 to t of Prx dx. Okay, so it is equal to, instead of Px, we replace it with this value. We use Px, not Pt dt, because we have t in the integral limit. So like there is no difference between like if we say Pt dt or Px dx. In order to make them separate, we use the variable t for time here in the integral limits and variable x for the power. So it's equal to integral of 0 of t Ria square over 2 plus Ria square over 2 cosine of 2 omega t. In fact, 2 omega x dx. Okay, because the first term, like it doesn't have x, it is a constant, we can remove it from the integral and separate the integral to two parts. So we can say it is equal to integral of 0 of t Ria square over 2 dx plus integral of 0 of t r I a square over 2 cosine of 2 omega x dx, which is equal to r I a square over 2 integral of 0 of t dx plus integral of 0 of t. Uh, Let me just move the constant part out of the integral. Integral 0 of t cosine of 2 omega x dx, which is equal to r I a square over 2. Of course, this one is x between 0 and t, which is t, plus r I a square over 4 omega sine of 2 omega t, because we know that the integral of cosine of alpha t is equal to 1 over alpha sine of alpha t, and here the alpha is here alpha is 2 omega, which is equal to r I a square over 2 t plus r I a square over 4 omega sine of 2 omega t. So this one is the energy delivered to a resistor in sinusoidal steady state circuits. So let me box around it. Okay. And so we have the energy, and of course we have the power. So this one is the power, and this one is the power, and this one is the energy. Okay. So if we graph these two variables, energy and power, for the resistor in steady state circuits, for power we will have this graph. So P R of t, and here is time domain, and we know that power is equal to RIA square over 2 times 1 plus cosine of 2 omega t. So if we plot it, we will have this graph. The maximum of this graph, of course, is when cosine of 2 omega t is maximized, which is 1. 1 plus 1 is 2, and the 2 times ri square over 2 results in ri a square. Okay, so the maximum value amount for this for the power is ri square. So the maximum is RIA square. What is the minimum? Of course, the minimum like happens when cosine of 2 omega t is the minimized, which is -1. So it is equal to 0, as you see. So this one is the power. Let's show the energy. for energy we say omega r of t over time, and for the energy we know that energy is equal to r I a square over 2 plus r I a square over 4 omega sine of 2 omega t. And if we graph this equation, we will have this curve. Okay, so this one is the energy. We should notice that both of the power and energy are positive. Both of the energy and so I missed the t here. So here I missed the t here. So I added like t, and so this one, this part shows that how the energy is accumulating and increasing over the time, and this like part shows this alternating this value over the time. Okay, so both p power and energy for the resistor both are always positive, okay, while energy increases without any bound, so increases without bound. Okay, so it reminds that this reminds that a resistor is a passive element which dissipates energy. You see, the energy is dissipating over the time. So by as long as we keep our circuit running with the passive elements like a resistor, the energy will be like the dissipated energy will be increased. So it shows that resistor is a passive element which dissipates energy. Okay, now that we know power and energy in a resistor in a sinusoidal steady state circuit, we need to discuss the same parameters of energy and power for inductor and capacitor. Okay, first for inductor. For the inductor, in sinusoidal steady state, we have a sinusoid current IL of t, which is equal to IA cosine of omega t. It's the current passing through like the inductor. We know that for inductor, energy is equal to half of L ILT square. Okay, we already discussed this relationship in chapter for inductor and capacitor. So we know the energy of inductor is half of Li square. So it's equal to 1 over 2 L. Instead of current, we replace it with this value. It is Ia square cosine of omega t square. Okay, it's equal to 1/4 of L Ia square 1 plus cosine of 2 omega t. Okay, so this one is the energy, omega L of t. the energy of an inductor. Okay. Now what about the power? We know that power is derivative of energy. So PL of T is equal to derivative of energy over time, which is equal to, so we need to calculate the derivative of this term. Okay, so this term, of course, this term can be expanded to two terms. One term which is like the constant, and the other term which is like the product of cosine of 2 omega t and this constant. For the first part, because it's the constant, of course the derivative is 0, so we will have a power equal to negative omega L I a square over 2 sine of 2 omega t. So this one is the power. So we have the power and energy in an inductor. Okay, so we want to graph these two signals to see how are these signals in inductor. Let's graph power. If we look to the power, we see that it is a sinusoidal signal with the maximum minimum value of negative omega L I a square over 2. So the maximum value is omega L I a square over 2. The minimum value is negative omega L I a square over 2, and because of this negative sign, the sinusoid, this is like sine signal starts from negative origin, so it will be this graph. Okay, and let me just put some dashed lines here. Okay, okay, this one is the graph for power. For the energy, we graph the energy omega L of t over as a function of time. If we look to the energy equation, we see that it has a sinusoidal part and it has a constant part, which shifts the graph like to the positive uh, side of the graph. Okay, so what is the maximum value of this term? The maximum value, of course, is when cosine of omega cosine of 2 omega t is equal to 1. So the maximum value of this term will be 1/4 of Li square times 2, which is 1 over 2 omega 1 over 2 Li square over 2. So the maximum of energy is Lia square over 2. Minimum is 0, and the graph is like this. Okay, so this one is the energy. Okay, some conclusions from these two figures. So let's see what we have. The first thing is both PL of t and omega L of t are periodic function. Okay. The second, we see that power is alternately positives and negative. So power is alternately positive and negative. The third conclusion, omega energy is always positive. Energy is always positive. This one is the third conclusion. So as energy is always positive, the inductor does not deliver net energy to the rest of the circuit. Okay, because as the omega L is positive, the inductor does not deliver net energy to the rest of the circuit. So we can say that the inductor does not dissipate energy. So we can say inductor does not dissipate energy. Okay, if we look to the power graph, we see that the power alternates signs, so the inductor like stores energy during the positive half period, half cycle, and returns the energy during the next negative half cycle. So if we look to the power, we can conclude that the inductor stores energy during the positive half cycles and returns the energy undiminished. Nothing changed. Exactly the same energy during the next negative half cycles. So we can say that in a sinusoidal steady state, there is a lossless interchange of energy between the inductor and the rest of the circuit. The lossless interchange of energy. If you look to the energy graph, we see that energy like energy goes like it starts from maximum value goes to zero, the energy of the inductor, and then goes up, the energy dissipated. So again the energy goes to zero, it goes up, and if we run the circuit for a long time, still the energy dissipated, or the total energy, is between this value and the zero. But if we look to the resistor, we see that the energy is like continuously increasing. So for after a long time, we will get like energy dissipated in a resistor. But in inductors, we see that the energy always interchanged between is interchanging between the circuit and the inductor. It means that if we have an ideal inductor and if we connect it to electricity outlet in in our home, absolutely no energy bill we will receive for this inductor, because the same amount of energy that the inductor gets from the electricity network in the first half cycle, it returns to the electricity network in the second half of the cycle. But it has to be an ideal inductor. Okay, we will discuss it in detail later about energy networks, but for now Fifth conclusion, we can say inductor stores energy during the positive half cycle, and then returns the energy undiminished during the next negative half cycle. Okay, and the last conclusion is we can say in sinusoidal steady state, there is a lossless interchange of energy between an inductor and the rest of the circuit. Okay, so these are six conclusions that we have based on the energy and power in an inductor in a sinusoidal steady state circuit. Okay, so let's go and move and discuss the energy and power in capacitor. So capacitor, for capacitor, we know that the voltage across a capacitor in sinusoidal steady state circuit is VA cosine of omega t. And of course, the energy in a capacitor is 1 over 2 C VCT square, which is equal to 1 half of C VA square cosine of omega t square, or 1/4 of CVA square 1 plus cosine of 2 omega t. So this one is the energy in a capacitor. What is the power in a capacitor? Power, we know that the power in a capacitor is derivative of the energy, so it's d over dt of energy of a capacitor, which is equal to negative omega CVA square over 2 sine of 2 omega t. So this one is the power for a capacitor. And if we graph power and energy, the same thing we did for inductor, if we repeat the same thing for a capacitor, we will have these results. This one is the power in capacitor, and for energy we will have this graph. Again, the same conclusions that we had for inductor, we have the same conclusions for capacitor. And in summary, we can say from figures, power is sinusoidal, and there is a lossless interchange of energy between the capacitor and the rest of the circuit. Okay, so we have our power and energies determined in all elements for sinusoidal steady-state circuits. Now we want to discuss average power. Average power. So as we saw, the power delivered to any of these three elements, resistor, capacitor, and inductor, like all of them is like a periodic function. All of them are sinusoidal functions. So we can describe them by an average value. Okay, we can describe them by average value, and for any average value we can calculate it by integraling the function over one period of periodic functions. So we can say the average power in sinusoidal steady state is defined as P is equal to 1 over T0, which is one principal period, integral of 0 to T0, P of T dt. We know that for sinusoids, for any sinusoid signal, the average is equal to 0. Okay. Why? Because the area under alternate cycles cancel. So we can say the average value of any sinusoid is 0, since the area under alternate cycles cancel. Okay. If we look to inductor and capacitor, if we look to inductor and capacitor, we can see that both of them have a sinusoid power. This one is for capacitor and this one is for inductor. Okay, so both of them have a sinusoid signal with no offset, and so we can conclude that the average power for inductor PL average is equal to 0 and PC average is equal to 0. If we integral those two powers, the result is 0. But what about the resistor? The resistor, we know that in the resistor we have both a sinusoid AC component and a constant DC component. If we look to resistor, yes, here. Uh, yes, here. If we look to a resistor, we see that it has both DC component and AC component. Okay, so the average is not equal to 0 because it has both DC component and AC component. So let's go back to our calculations here and see what is the average power for resistor. For resistor, the power is equal to, as we just saw, it is equal to RIA square over 2 times 1 plus cosine of 2 omega t, which we can write it in this form, RIA square over 2 plus RIA square over 2 cosine of 2 omega t. So we see, you see that we have both DC component and AC component. Okay, so of course the average for AC component is 0 and the average for DC component is like the value of Ri square over 2. So we can conclude that the average power of a resistor in sinusoidal steady state circuit is 1/2 of RIA square. So this one is the average power of a resistor. So the average power for inductor and capacitor are 0, but for resistor is 1/2 of Ri square. So how if we just calculate the integral of this function for one period, we see that the answer will be equal to RIA square over 2. So okay, let me just go here. So let's now that we know what are the average powers for all in elements, let's discuss the average power delivered to like a arbitrary load. Let's say we have an arbitrary load. Of course, the load is ZL, which is a complex number which has two components. If you remember, I said that it has the resistance and it has like the real part and imaginary part, which the real part is called the resistance and the imaginary part XL is called the reactance. Okay, so in order to find the average power delivered to this load, what we can do, first we need to find the current through this ZL with different analyzing methods that we learned so far, mesh analysis, Thevenin node super position node analysis. We need to find the current going through this load, and then we can simply find the average power. But one thing which is important. Let's assume we have the circuit and we found IL. Okay, so what is the average power? As I mentioned, we know that the reactance part represents the net inductance and capacitance. If you remember, when we discussed the equivalent impedances and the like impedances in general, I said that XL, the reactance, represents inductors and capacitors, and RL represents resistors. Okay, so the ZL is built from one resistor, one inductor, and one capacitor, something like this. The total of capacitance and inductance generates XL, and the resistance is related to RL. Okay, so as we discussed a few minutes ago, we said that absolutely the power dissipated. We saw that there is absolutely no power dissipated in the inductor and the capacitor. So when we have the load, we know that the reactance part doesn't dissipate any power, doesn't use any power. The average power is 0 for the reactance part. And the only part which has the power not equal to 0 is the resistance. So when we got the IL, okay, we are supposed to use this equation. We know that P is equal to RZL square. Okay, RZL square. But we know that this ZL, which consists of two parts, we know that the reactance part doesn't have any power. The average power is 0. So instead of writing ZL in our equations, as we know the power for reactance part is equal to 0, we say power is, oh no, sorry, here is not RZL. I meant ZLIL square, sorry. Okay, but here, as I mentioned, we know that the ZL has two components, real part and imaginary part. The imaginary part is the reactance has a power of 0. So instead of this equation, we can just write it in this form. P is equal to 1/2 of R L I L square. Okay, so this one is like the power in a steady state sinusoidal signal with a complex or complex load. So just remember this equation. Just remember this equation, and whenever we have a circuit, we need to find ZL. When we found the ZL, we know that the ZL has two components. Ignore the inductance and consider RL. Then find the current going through the resistor, going through the load, and when you got IL, use this equation. P is equal to 1/2 of RL IL square to find the power. Okay. The last thing I want to tell about the power is that if you remember, when we have a circuit, in order to find the total voltage of current at any point, we can use a superposition. Okay, we can use a superposition to find the current or voltage and at any point. But for powers, when a circuit contains two or more sources, superpositions superposition applies only to the total load current and not to the total load power. I mean that when we have a circuit here and we want to find the current at this Ix, the current at this resistor, we can use superposition. But if we are supposed to find the power in this point, we cannot use superposition. Okay? So this one is just one like a hint. If you have any, I gave you any like problem to solve and ask you to find the power dissipating in one point of the circuit. Of course, in order to find the Thevenin equivalent or other methods, we can use superposition. But for finding the power, we cannot use superposition. Okay, so let's see some examples. Example, find the average power delivered to the load to the right of the interface. here is the circuit. We have a voltage source with a value of 150, the angle of 0. We have a resistor 50. We have an inductor J250. Then we have a capacitor here, negative J75. And finally, we have a resistor here with a value of 100. Okay, and the interface is here. We want to find ZL on this point, and let's start solving this equation. So because we want to find the average power delivered to the load to the right of the interface, we need to consider the inductor, resistor, and 100 ohm, inductor, capacitor, and 100 ohm resistor, because this 50 ohm resistor is on the left of the interface. So we find the equivalent circuit to the right of the interface. So let's find the total impedance as a load. So we can say ZL is equal to negative J75 parallel with 100 and series with J250. These two are in parallel, and the equivalent value is in series with J250. It's equal to J250 plus negative J75 times 100 over 100 minus J75, which is equal to 36 plus J202. If we convert this value to polar form, it will be equal to 205 angle of 80 ohms. Okay, so this one is ZL. Now we simplify the circuit in this form. We have the voltage source 150 with the angle of 0, 50 ohm resistor, and we have ZL, which is equal to 205 with the angle of 80 or 36 plus J202. We find the current IL. IL is equal to 150 with the angle of 0 over 50 plus 36 plus J202, which is equal to 0.683 with the angle of negative 67 amp. So this one is the current, and then we can say the average power delivered plus the interface is, we use this equation, which equation? This equation. P is equal to 1/2 of RL IL square, which is equal to. So when we put like anything in the absolute value, it means that if the number is complex, we only consider the amplitude of the number, or amplitude of the value, not the phase. Okay, so the absolute value of this current is equal to 0.683, because its absolute value includes only the amplitude, not the angle or the phase. So it's equal to 1/2 times. So 36, which is the real part of the load impedance. So no matter what is the reactance of the load, nothing gonna change. Okay, so because the average power of the reactance part is zero, so the only thing matters is the resistance part. So from this ZL, we only consider the real part. So it's 1/2 of 36 times 0.683 square, which is equal to 8.4 watt. We should know that all of this 8.4 watt goes into the 100 ohm resistor. Why? Because the inductor and capacitor do not absorb average power. Okay, let me write it down. Note, all of this power goes into the 100 ohm resistor, since the inductor and capacitor do not absorb average power. Okay. The next example, let's assume we have this circuit and it says using superposition find average power delivered to the 20 ohm load. Here is the circuit. plus minus 100 cosine of 10 to the power of 4t 1 millihenry 20 ohms 1 microfarad. The current source 10 sine of 10 to the power of 4t, and that's it. So let's just remind one thing. I said that we cannot use superposition to find the power delivered to this load from each individual sources and then add the powers. Okay, it's not gonna work. What we need to do, we need to find the currents delivered to this, not delivered, the current going through this resistor as a function of each individual source. When we got the current, we find the power. Okay, we cannot directly find the power. I will show it to you now. First thing we need to do is converting this sine to cosine. So it is equal to 10 cosine of 10 to the power of 4t minus 90 degree. And let's convert this circuit to phasor, and we will have J10 20 negative J100 10 with the angle of negative 90 100 with the angle of 0, and of course omega is 10 to the power of 4. Okay, for both of them omega is set. So superposition. First, let's turn off the current source. The circuit will be in this form. 100 with the angle of 0, J100, 20, and we want to find IL. Yeah, IL. So I should just call it IL. L is not inductor, it's load. IL. So IL1. Since the one terminal of the capacitor is open, so the capacitor is off the circuit, and in order to find the current, we can simply say IL1 is equal to the voltage over the impedance, which is 20 plus J, it is J10. Here was J10, I wrote J100. 20 plus J10, which is equal to 4.47 the angle of negative 26.6. Okay, so this one is IL1. So now that's here is the point. When we got IL1, we cannot find PL1 at this point, and then add those powers. So it's not gonna work. Okay, so this, when I say that we cannot apply superposition to find the power from individual sources, I mean this. I mean that when we got the current, we cannot directly find the PL1 here and find PL2 later and add these PLs. No, it's wrong. What we need to do, we need to find IL1 as we did, then we need to find IL2 and then add those two currents, find IL, and then find the power. So now turn off voltage source. Here is the circuit. J10, 20, negative J100, 10 with an angle of negative 90, and this side we have short circuit. So we want to find IL2. Okay, in order to find IL2 using mesh analysis, we have two loops, I1 and I2. For loop 1, for loop 1, J10 I1 plus 20 I1 minus I2 is equal to 0. Loop 2, I2, if we look, we see that we have a current source in the loop, so we say the current is equal to the value of the current source. So it's negative 10 with the angle of negative 90. So we can write these two in this form: 20 plus J10 I1 minus 20 I2 is equal to 0, and of course I2 is equal to negative 10 with the angle of negative 90. If we calculate or solve these two equations, I1 will be equal to 8.9 with angle of 63. Okay, we got I1 and I2, but we want to find IL2. What is IL2? IL2 is I1 minus I2. So we say IL2 is equal to I1 minus I2, which is equal to 8.9 angle of 63 minus negative 10 with the angle of negative 90. IL2 is equal to 4.5 angle of negative 27. Now that we got IL1 and IL2, we can say the total current IL is equal to IL1 plus IL2, which is equal to 4.47 angle of negative 26.6 plus 4.5 with the angle of negative 27. IL is equal to 9 with the angle of negative 26.8. Now that we got the IL, we can calculate the average power. So we can say the average power is equal to 1/2 of RL IL square, which is equal to 1/2 of 20 times 9 square, which is 810 watt. So this one is the average power delivered to 20 ohm resistor. So now that we can calculate the average power in load, it's time to see what is the maximum power available to a load in sinusoidal steady state circuits. So in DC circuits, we know that the maximum power is V Thevenin square over 4R Thevenin. But let's see what is this value in AC circuits. So we want to discuss maximum power in AC circuits. Okay, so in AC circuit, we have a Thevenin equivalent voltage source. We have Z Thevenin and we have ZL. By knowing the values of Z Thevenin and V Thevenin, we want to know on the what is the maximum power which can be delivered to ZL and what should be the value of the ZL to receive the maximum power. Okay, so how we find Z Thevenin and how we find the Z Thevenin and V Thevenin in this circuit. Of course, we have different methods that we discussed before. We can find V Thevenin and Z Thevenin. Okay, so what is Z Thevenin? Z Thevenin is equal, of course, consists of two parts. It's R Thevenin, which is the real part, plus JX Thevenin, which is the reactance part, which is imaginary in this impedance. For the load, we have ZL equal to RL plus JXL. Okay, so the goal, the objective is to adjust the load impedance RL and XL so that the average power to the load is a maximum. So the goal is, so let me just write it here, the objective or goal, the objective is to adjust load impedance RL and XL so that the average power to the load is a maximum. Okay, we know that the average power delivered to load, as we discussed, is equal to 1/2 of RL I square. So the amplitude of the current square. What is I? The absolute value of I. If we look to this circuit, what is the absolute value of I? Using Ohm's law, we know that the I is Thevenin over Thevenin plus ZL. Okay, so we can say the absolute value of R can be written in this form: Thevenin over Thevenin plus ZL, which is equal to Thevenin over, we like expand this Thevenin and ZL to real and imaginary parts. So we will have R Thevenin plus RL plus J X Thevenin plus XL. Okay, so I is equal to Thevenin. What is the amplitude of denominator? Of course, the amplitude of denominator is the square root of real part square plus imaginary part square. So we can say it's equal to square root of R Thevenin plus RL square plus X Thevenin plus XL square. Now that we got I, we can replace this value in this equation. So we will have P is equal to 1/2 of RL Thevenin square over R Thevenin plus RL square plus X Thevenin plus XL square. Here we know that the values VT, Thevenin, and R Thevenin and X Thevenin are fixed. Okay, and we want to select RL, we want to select RL and XL to maximize the power. Okay, to maximize the power. Definitely, in order clearly for every value of RL, the denominator is minimized and the power is maximized when XL is equal to negative X Thevenin. I mean that if we keep this part of this denominator equal to 0, of course the power will be maximized. So we try to keep this like part, which is x Thevenin plus xl square equal to 0, because it is definitely a positive number and we want to keep it as minimum as possible. So the minimum possible value for a positive number, of course, is 0. So we say that clearly for every value of RL, the denominator is minimized is minimized and P maximized when x Thevenin plus xl square is equal to 0, or xl is equal to negative x Thevenin. Okay, so the first like conclusion, our goal was finding R Thevenin and X Thevenin. Sorry, RL and XL. We got the XL. XL should be equal to negative X Thevenin in order to have a maximum power. So if XL is a if XL is equal to negative X Thevenin, the power will be equal to 1 over 2 RL V Thevenin square over R Thevenin plus RL square. Now we want to minimize this value. We want to find RL in a way that the value is minimized. Of course, RL cannot be 0, because if RL is equal to 0, the total power will be equal to 0, because we have an RL here, and we cannot simply say, okay, let's just have, we cannot do the same thing we did for XL. So for RL, we cannot set RL equal to 0, because it gives the power equal to 0, which is obviously it's not the maximized power. So in order to find the maximum value of this term, we know that the function is maximized when the derivative of this function is equal to 0. So if we calculate rho p over rho rl and equal it to 0, the result gives the maximum power. So if we do this and calculate the derivative of this equation, we will see that P is maximized when RL is equal to RT. Okay, so we got the answer. So in summary, to obtain the maximum power transferred in a sinusoidal steady state. We select XL equal to negative X Thevenin and RL is equal to R Thevenin. So ZL is equal to RL plus JXL, which is equal to R Thevenin minus JX Thevenin. Z Thevenin, of course, is equal to R Thevenin plus JX Thevenin. You see, if we compare these two, we see that the real parts are same and the imaginary part have a different sign. So we show the ZL with this symbol. So it is ZL is equal to Z Thevenin asterisk. We call it a conjugate match. So this one is a conjugate match. So ZL should be conjugate of Z Thevenin in order to have the maximum power. So let me say if we have X equal to A plus JB, X conjugate is A minus JB. Okay, this one like is a conjugate. So the load should be conjugate of the Thevenin uh, load in order to have the maximum power transfer to the function. So if we replace, if in this equation we replace, not in this equation, in this equation, if in this equation we like replace ZL with Z Thevenin conjugate, we will have P is equal to 1/2 of RL V Thevenin square over R Thevenin plus RL square plus Z Thevenin plus ZL square. So if we replace ZL with negative Z Thevenin and RL with R Thevenin, we will have power is equal to 1/2 of RL V Thevenin square over 2R Thevenin square plus 0, which is equal to V Thevenin square over 8R Thevenin. So P max is equal to V Thevenin square over 8R Thevenin. This one is the maximum power delivered to a load. Let's see one example. example. Example has two parts. Part A, calculate the average power delivered to the load if ZL is equal to 200 ohms. Part B, is calculate the maximum average power available at the interface and specify the load requirement to draw the maximum power. Okay, so first we want to find the average power, and then we want to calculate the maximum power, maximum average power available for this circuit, and specify the load requirement. Here is the circuit. Vs of t is equal to 5 cosine of 10 to the power of 60. (200.01 microfarad ZL, and that's it. This one is the circuit. The first thing we should do is finding the phasor equivalent of this circuit. We draw the circuit in phasor mode. So in phasor we will have this circuit plus minus 5 with the angle of 0, omega is 10 to the power of 6, 200 ohms resistor, negative J 100 ohm capacitor. We have ZL, and here is the circuit. So what we need to do now at the first step, we need to find the Thevenin equivalent seen from the load. So for Z Thevenin, we turn off the voltage source and remove the load from the circuit and look to the circuit from these 2 points. Z Thevenin is equal to 200 in parallel with negative J 100, which is equal to negative 200 J 100 over 200 minus J 100, which is equal to 40 minus J80. This one is the Z Thevenin. For V Thevenin, we bring back the voltage source. We know that the V Thevenin is voltage here, which is the same as voltage across the capacitor. So V Thevenin is equal to, the easiest way is like voltage division, negative J100 over 200 minus J100 times 5 with the angle of 0, which is 1 minus J2. Or if we write it to polar mode, in polar mode is 2.24 with the angle of negative 63.4 volt. Now that we have both V Thevenin and Z Thevenin, let's draw the equivalent circuit. Here is the equivalent circuit. V Thevenin, which is equal to 2.24 with the angle of negative 63.4, and we have a Z Thevenin, which is equal to 4D minus J80, and of course we have ZL. This one is equivalent circuit. So it says that find the average power if ZL is equal to 200 ohms. So how we can do that? We can simply find it by finding the current. The current is part A, in fact. Current is equal to V Thevenin over Z Thevenin plus ZL, which is equal to 2.24 with the angle of negative 63.4 over 40 minus J80 plus 200, which is equal to 8.84 with the angle of negative 45 milliamp. Okay, so we got I, we have ZL, so we know that P average is equal to 1 over 2 RL, which is the real part of the load, times I square, which is equal to 1/2 of 200 times 8.84 times 10 to the negative 3, because milliamp square. So P average is equal to 7.81 milliwatt. So this one is part A. Part B. Part B says what is the maximum average power available at the interface. The maximum power available at the interface is equal to P max is equal to V Thevenin square over 8 R Thevenin, which is equal to 2.24 square over 8 times 40, which is equal to 15.6 milliwatt. So you see that the maximum the maximum average power is 15 milliwatt, while we get only 7.8 watt. So how we can get the maximum power under which conditions? We know that the load should be uh, conjugate of the Thevenin impedance. So in order to have the maximum power, ZL should be conjugate of Z Thevenin. Z Thevenin, we know that it is equal to 40 minus J80, so ZL should be 40 plus J80. Okay? And if we, what is this circuit? It has a resistor and it has an inductor. Okay, because it's the reactance is positive, so ZL should be a resistor with a value of 40 ohms and an inductor with the value of J80. So if we want to build this circuit in the lab, we don't have J80 Henry, so we should convert it back to time domain. So we know that L, of course, is equal to J omega is not L, ZL, XL is equal to J omega L. So if we use these equations, we say J80 is equal to J omega is 10 to the power of 6 times L. So J cancelled by J, and as a result, L will be 80 over 10 to the power of 6, which is 80 microhenry. So we need to have this circuit, this load. RL is 40 ohms and L is 80 microhenry to have the maximum power delivered to this load in this circuit. Okay, so that's enough for today. In the next lecture, I will solve one more example of this maximum power, and then we continue our lectures.